Let's begin. Welcome again for another installment of Computational Fluid Dynamics 2024. We are pretty much done with the first part of the course to get you to solve the Navier-Stokes equations. We learned two methods. Finite difference method, which resulted in a diverging or non-divergence-free velocity field. And then we pivoted to the staggered grid, which naturally led to the finite volume method, which is conceptually going to be more effective for computational fluid dynamics problems as we build our knowledge for the rest of the semester. For part two, we are going to start digging deeper into the weeds, behind the scenes. Why did we see oscillations when we were running central on advection, for example? Yeah, we kind of dabbled with that a little bit with stability, but we're going to look at more mathematical tools to understand what's going on there, how to fix that. But there was a low-hanging fruit that you probably observed when you were running your projects. One of the reasons you didn't run to long times was that it was taking a long time, and it was because of the pressure solver, of the iterative solver. In fact, half of my research at the University of Utah is centered on figuring out ways to avoid having to use the linear solver for the pressure. Okay? So Maher's research is on finding ways to conserve mass without solving for the pressure. So we avoid that big linear solver. And in practice, in many cases, that pressure solve could cost anywhere between 70% of the calculation, the total calculation, down to 30% when you have a lot of physics going on, but it's a pretty big piece of the computational fluid dynamics cost when you think of computational cost. So as we get into part two of the course where we're gonna dig under the hood, I figured that would be a good segue is to start with with linear solvers and start by asking the question, can we make the linear solver faster? So we can get faster solutions and reasonable solutions for these problems. In my undergraduate numerical methods, when I talk about linear solvers, I explain direct methods and iterative methods. And I explain Jacobi and Gauss-Seidel and SOR. And many students, and in undergraduate numerical methods, you're talking about systems maybe 100 by 100, 100 equations, 100 unknowns, or like 1,000 equations. And if you use A inverse or the built-in tool, you solve this matrix once, it takes you a fraction of a second, right? 1/10 of a second. That's fine, right? But then I tell them, even that 1/10 of a second, you put it over 100,000 time steps, or 1,000,000 time steps, that is going to amplify and consume a considerable amount of time. Because that 1/10 of a second is the equivalent maybe of 50% of the total cost in a single time step. And it's not until you get to solving PDEs or doing CFD that you see the immense cost of linear solvers. So in the next couple of lectures, 2 to 3, I hope we finish in 2 lectures, we will start digging deeper into iterative solvers or linear solvers in general, discuss the theory of iterative solvers, look at why Jacobi and Gauss-Seidel and SOR, why one is faster than the other, when does SOR behave better than the others. We're going to learn a few technical terms along the way. So it's one of the nicest lectures that I like to give on iterative solvers. Okay. I will start with the problem that we're familiar with when we interacted with linear systems of equations, and that's with the Poisson equation. So either steady state heat transfer, which was the 1D heat transfer problem we did at the beginning on the rod, or the Poisson equation for the pressure in 2 dimensions, right? They're just the same problem, but in 1D or 2D, and we're going to extend it to 3D today. That's one example where we recovered a linear system of equations. And I like to focus on elliptic equations because, again, I'm going to tie this into the pressure, which is an elliptic equation. Mathematically, that means that if you make a change in one place of the domain, it is going to be felt instantaneously at every other location in the domain. So that's what elliptic partial differential equations mean. And that makes sense because the pressure needs to adjust itself to make sure it conserves mass if there's a change in mass conservation at any other location in the domain, right? You open a valve, instantly it's going to figure everything out so that mass is conserved. And this typically arises when you apply a conservation law, which is divergence, on a quantity that is proportional to itself. So essentially, when this flux, like heat flux, for example, is k grad phi, you apply the divergence to that, which is a conservation law conserving the flux over a control volume, you get, there's a typo here, this should be div k grad phi. I should lose points on that because that's kind of the mistake I was telling everyone to avoid. So my bad here, I apologize. So this should be div k grad phi. If k is constant, you get the Laplacian, but this is still a type of Poisson equation, okay? Now, you see how this would lead to a linear system of equations when you discretize this on a grid and you do central differencing, for example, you get the relations between discrete points. And so this equation immediately in your mind should resonate, should be the equivalent of a linear system of equations. There are other examples of elliptic equations, steady state conduction, 2D stream function, vorticity stream function formulation. We didn't study that, but if you've taken fluid mechanics, you'd remember this. Pressure projection, steady advection diffusion problem, you'll get a linear system of equations. Biharmonic equation, which is like a fourth order elliptic equation. So, you get a lot of places where you see elliptic equations. We were interacting with this and this so far. Because we can do all of those, they're just the same strategy. And in the end, they all end up in systems of linear equations. And in general, we write a linear equation for an unknown quantity phi as once you write the equations at every point, you get a relation between the variables at those points and the neighboring variables, right? And they're multiplied by coefficients. So you write all the equations starting from point 1, 2, 3, etc. This could be in 2D, 3D, okay? It still always results in a matrix. And so you write those equations, you put the coefficients aside, and that you get a matrix multiplying a solution vector equal to some right-hand side values. Implicit methods also will result in systems of equations. They are in general nonlinear, but then we approximate the nonlinear system by linearizing it, so you always end up getting to linear systems of equations. We didn't cover that in class yet, but we'll touch on it when we look at more advanced Navier-Stokes solvers. But right now, I just want you to keep in mind that, yep, we have linear systems of equations. And once you have systems of equations, I tell my undergrad students, you need to abstract it, write it in matrix form, because when you write it in this form, turns out just reasoning about this coefficient matrix tells you a lot about the system. And vice versa, every time I see a matrix, I immediately connect the matrix to a linear system of equations. A matrix is not an array. Be careful. Okay, a matrix is not an array or field or something. No, a matrix is associated with a system of linear equations, ties in unknowns with the other unknowns together with these coefficients, all right? So it's a very special type. It looks like an array, but that's just a coincidence, okay? All right, so how do we solve this? We say A phi equal B, and then phi is A inverse B, right? And so, okay, that's kind of what we've always learned, how to solve a linear system of equations, or at least write it mathematically. Now, the goal of linear solvers in general is to do one of the following. Either find the inverse of A, which is a very expensive proposition, and we will demonstrate that in your homework. Find an approximation to the inverse. Okay, so these are methods where you find an approximation to the inverse and then just use that inverse to solve the system. Or find the solution of the system without explicitly computing the inverse. And we're like, can we really do that? Well, yeah. What is SOR? Or Gauss-Seidel or Jacobi? We solved for the unknowns without computing the inverse, right? We kind of inverted each equation locally, but we never got to compute the inverse. We never touched that inverse, right? So those are the methods that we will be looking at, comparing them to methods where we find the inverse or directly solve the system of equations. All right. Now, before I get into the weeds, I want to define and introduce a topic called computational complexity. For any algorithm, think about SOR or Jacobi or Gauss-Seidel or even the code that we wrote in class. we distinguish between two types of complexities. What is complexity is essentially how difficult is this problem to solve. That's just a simple way of saying it. There's the fancy word is algorithmic complexity or computational complexity. There are two types of complexities in computational algorithms. There's time and space complexity. Okay. Time complexity is a measure of how long an algorithm would take to complete given an input of size n. What is size n? Number of equations, number of grid points, right? Okay. How long would it take for it to complete? So this is usually measured analytically by counting the number of floating point operations. That's it. So additions, multiplications, divisions, and subtractions. Even array accessing an element in an array, that will incur a computational operation, because in memory, the computer is trying to find where the location of that index is. So it's doing some internal calculations. So you can assign one floating point operation to a memory access, right? So that's why it's important to optimize an algorithm. But for time complexity analysis, you take the most optimum version of the algorithm, which essentially boils down to just counting the number of multiplications, divisions, additions, and subtractions, and scaling that to a very large number n. At small numbers, you're going to see a lot of fuzz, a lot of noise. But at large numbers, taking the Gauss-Seidel or the Jacobi or the SOR to a million or a billion equations, as n approaches infinity, how does that algorithm scale? Does it grow exponentially, polynomially, linearly, sublinear, right? Or does it stay flat? So that's an important measure of how an algorithm operates. You've probably seen that Gaussian elimination is order n cubed, right? Or like array sorting is n log n. There's an algorithm that does sorting of an array order n log n rather than n squared, right? So that's what I'm talking about. It's how fast the algorithm behaves as we scale the input. Okay, and that's a very important measure. We want to be linear or constant. Ideally, that's what we would like. All right? I'll show you a plot in a second. So if an algorithm has to scale, it should compute the result within a finite time, like I said. And so this reason complexity is measured asymptotically as n approaches infinity, right? Now, the next facet, the second facet of computational complexity is space complexity, and it simply refers to an algorithm's memory requirements. Like, what do we need to store in memory to achieve the algorithm, right? So do we need to store every array that we're dealing with? Or with linear solvers, do we need to store the matrix, all the elements in the matrix, some of the elements in the matrix, or none at all? So consider, for example, the successive over-relaxation or Jacobi. We never stored anything about the matrix. We just evaluated on the spot. So our only memory requirement was storing that array for the solution variable, right? That was the only space complexity for that problem. Okay. Now, this is a plot showing this time complexity and telling us where we are bad and where we are good and where we are better, okay? So that straight line, so what you're looking at here is the number of operations or the order of algorithm. This counts the number of floating point operations versus the input, number of entries. So think of this as number of equations or number of grid points. You see here, this is order n factorial, horrible scaling, order 2 to the power n, order n squared, and then this would be order n, which is just right at the straight line. Order n log n is better. Sorry, this is order n, order log n, order 1, which is kind of flat over here. And so this region is horrible, no good, okay? No good. This region is really, really bad. This should be order n over here. I don't know what's going on. Anyway, this is bad, this is fair, this is good, and this is excellent. So in terms of algorithms. Now, the standard method of using the A inverse, I want to tie this to linear solvers to explain to you why it was so costly, what we were doing, and why we need to avoid it. Gaussian elimination, which is the standard method to obtain the inverse of a system of equations or a coefficient matrix, scales as order n cubed. Okay, so it places it in this region, which is really, really bad. So, yes. Oh, sorry. Yeah. So, yeah. No worries. All right. Okay. Now, for linear solvers, as you noted in your projects, like I said, when you were trying to get the solution for long times, you complained that it was taking such a long time. Okay, so today we're going to look at both time complexity and space complexity of our algorithms, okay, and what we used so far. We will start with space complexity because it's a little bit more generic discussion, and then we get into time complexity and speak about different algorithms. So some of the common matrices, so for linear solvers, really, if you're taking A phi equal B, the space requirements are going to be dominated by A, okay, that big matrix. Not phi, not B, those are simple vectors. They can, at large scale, at large numbers of equations, those get shadowed by the matrix A. So it's useful to look at the different types of matrices that, I'm going to take this, let me remove this here. So I want to look at some different matrices. You've probably seen this before. A general matrix where all entries are non-zero, we call this a dense matrix. A matrix where all the entries are on the main diagonal and above it are called upper triangular matrices. So where you see missing elements, it's all zeros. Lower triangular matrix, main diagonal and lower, everything above it here is zero. Just a diagonal matrix where everything is zero except the main diagonal. Identity matrix. And banded matrices where only a few diagonals are non-zero. If you remember the heat transfer in a rod problem, where we had the main diagonal first upper, first lower, we call that a tridiagonal matrix because it only has the three main diagonals are non-zero, everything else is zero. Now, you will also notice that when we go to the Poisson equation in 2D, we add one more diagonal here, one more diagonal there. We get a pentadiagonal system. Everything else is zero. And then when you go to 3 dimensions, you have to add two more. So we had east, west, north, and south. And you have top and bottom in the z direction. And then that will add 2 more diagonals. So you get 7 non-zero diagonals. So you see these banded matrices. And for structured grids especially, they dominate computational fluid dynamics, and specifically that equation for the pressure. So this is a very useful matrix to consider, the banded matrix. Okay. Now, given that, you will observe that, and in reality, in practice, for many cases we deal with in computational fluid dynamics, systems we deal with sparse systems of equations. So what is sparsity? It's anywhere where the number of zeros in the matrix dominates the matrix. We're going to define that more accurately in the next slide. And so these sparse systems have most zeros in the matrix. Now, when you write the equations themselves, you don't see that. When you write them in matrix form, you get to see that, right? So that's the benefit of abstracting systems of equations as a coefficient matrix, okay? So you get to see all of those zeros. And then the idea, so we're inclined often to store everything in the matrix, put it in memory. Remember, we're talking about space complexity, right now. So it's about storage. But the idea of sparse systems, like, do we really need to store those zeros? Like, there's thousands of zeros. They're mostly dominated by zeros, okay? So do we really need to store them? Why not? Why can't we think of a way maybe we don't store them somehow? Okay, so that's what we're going to work with now and compare the two. So, so the idea is if instead of storing all of the zeros, we only store the non-zeros along with the row and column they belong in so that you know where you are in the matrix. And then for k non-zeros per equation, this reduces storage from n squared to kn. I'm going to guide you through the math in a second. And for small n, it doesn't matter. So that's why you don't see this problem in numerical methods. But when you get to large number of equations, go to 2D or 3D, things are going to explode. Okay? So I'll start with this simple example that we did in class at the beginning of class, where we had this steady state one-dimensional heat transfer problem. In one dimension on a rod, we fixed the temperatures on the left, on the right, and we solved this steady state diffusion equation. And once we discretized everything and put our variables here, we ended up with this banded tridiagonal system. Everywhere it's zeros, except the main diagonal, the first upper, and the first lower diagonals. Okay? So now I'm going to focus on that matrix and start with some definitions. This is a sparse matrix. And we define sparsity for a matrix is simply the number of zero-valued entries divided by the number of divided by the total number of entries in the matrix. Okay? So if a matrix has 100 entries in it and there's 20 zeros in it, right? So it would be 20 over 100. If there's 70 zeros, it's 70 over 100, right? Just a simple count. Count the number of zeros and divide that by the total number of entries in the matrix. How do you know the total number of entries in the matrix? It's the number of equations squared, right? Because you have n equations by n unknowns, you get n by n, right? So it's n squared, yeah.
So in the upper and lower band, we have a 0 at the...
That doesn't matter. Because you're thinking about this as n goes to infinity, right? So that shouldn't matter, right? You don't count that. You say, and in fact, okay, so this is going to have n entries. If you remember, we did this exercise when we were programming it. This has n minus 1, and this has n minus 1. When we analyze things later, we're going to say this has n entries, this has n entries, and this has n entries. Because n minus 1 when n approaches infinity is n. Okay? So we don't worry about these minutiae. Even if there's a 0 there, it's going to be insignificant. Okay? It's not going to matter. And then we say the matrix is sparse if its sparsity is greater than half. In other words, if more than 50% of the elements in a matrix are 0, then the matrix is sparse. Okay, so you have 100 entries, 50 or 51 entries are zeros, then the matrix is sparse. Okay? So, in other words, if the matrix has more than 50% are 0, then the matrix is sparse. All right, so now grab your pen and paper or whatever, your laptop, and I want you to do this exercise with me. For a general tridiagonal n by n matrix, so you have n equations, n unknowns, and only 3 non-zero diagonals, main diagonal, first upper, first lower, okay? Develop a formula for the sparsity of that matrix. Remember, the sparsity is the number of zeros over the total number of entries in the matrix, okay? We know the total number is n squared. Just find the number of zeros. And then do that for n, and then calculate sparsity for n equal 100. So your sparsity formula will be as a function of n, or the number of equations, right? Take a minute. Think about that. So remember, the sparsity is the number of 0 entries divided by the number of total entries in the matrix. Here you know that the total number of entries is n squared. Okay? So how do you get the number of zeros? Do you know the number of non-zeros? We know that the 3 main diagonals are non-zero. So you can count those, right? And figure out the number of zeros. Go ahead and try it. This will be on your exam. What? This is a homework problem in undergraduate numerical methods. So if they can do it, you can do it. It's only counting. So count the number of zeros in the matrix for a general n by n matrix. So ask yourself, how do you count the number of zeros? Well, if you can, you know the total number in the matrix, and you know the number of non-zeros in the 3 diagonals. So you subtract that, you can get the number of zeros, right? Okay. Did you get it?
Well, I was trying to come up with it, but it didn't work out. But I
Did you get it? Okay.
Oh, I can see.
No, that's not right. Okay. All right. So here's the solution. We know that the matrix size is n by n, so it has n squared total entries. So we know that's going to be in the denominator, okay? Now, how do we count the number of zeros? I don't know that, but I know the number of non-zeros. I know on the main diagonal, I have n non-zero entries. On the first upper and first lower, I have n minus 1 entries each. So the number of non-zero entries is n plus n minus 1 plus n minus 1. Therefore, the number of zeros is n squared minus that, right? So that's the total number of non-zero entries. Everything else is 0. So what is the number of zeros? It will be n squared, or the total number of entries, minus this guy, which is 3n minus 2. Okay? So then you define the sparsity as that number of zeros, n squared minus 3n minus 2 over n squared. And then you plug in 100, n equal 100. Okay, what do you get? You get 0.97, or 97% of the entries, just for 100 equations. 97% of the entries in the matrix are zeros. Okay? So imagine storing that matrix and storing mostly zeros for no reason, right? Imagine this goes to 1,000 or 1,000,000 equations. Becomes 99.99% of the entries are 0. Okay? Okay. So now let's continue with this Poisson equation example. Okay? And I'm not going to move to the next slide. I'm going to expect answers from you guys. Okay? So you need to work your brain on this. All right? So we're going to take this Poisson equation. This still del squared p equal s. So in the 1D case, we had n equations because we had n grid points. Now we're going to assume n grid points in x, n grid points in y, and n grid points in z. So in the 1D case, we had n linear equations, and the matrix size was n by n, and we had only 3 non-zero diagonals. All right, can you do 2D? How many equations do we have in 2 dimensions? So I have a grid nx and y, nx equal ny equal n. So I have a grid with n points in the x direction, n points in the y direction. Finite difference, think just grid points. So how many equations will this result in? Okay, n by n, right? Because that's the total number of points in that grid. Okay? Okay? All right. Now what is the matrix size? Okay. N to the 4. You said n to the 4. So how did you get that? By n, right? So if the number of equations is n squared, the matrix needs to have n squared equations and n squared unknowns. So it will be n squared by n squared, right? Or n to the 4th, correct? Okay. No more answers, Jacob. Okay. What about the number of non-zero diagonals? 9? No. So think about the diagonals as the connectivity. When you're discretizing at a point, in 1D, we only had one neighbor to the right and one neighbor to the left, the east and west neighbors, right? For the central difference discretization. Now, we just did this with the Poisson equation. We had the P point, we had east and west, and north and south. So how many non-zero coefficients do you have? 5, right? So that is going to result in 5 non-zero diagonals, all right? Okay, what about 3D? Number of equations? So this is going to be n by n by n grid. So how many equations are you going to have? N cubed, right? So it's going to be n by n by n, exactly. Because you have one equation per point. Okay, one discrete equation per point. You have n cubed points, n by n by n. Okay, what is the matrix size now? So again, how many equations do you have? N cubed, right? How many unknowns did you expect? Okay, so what is the matrix size? It should be square. N cubed times n cubed, right? It needs to be a square matrix. The size of the matrix, same number of equations, same number of rows, same number of columns, right? So if you have n cubed equations, you expect to have n cubed unknowns. Your matrix is going to be n cubed by n cubed, right? This messes with your brain because everybody thinks that the matrix represents the grid. It doesn't represent the grid. It's not an array. The matrix represents the equations at each grid point. And if you're 3D, that's going to blow up. The matrix size is going to be huge. Okay, n cubed by n cubed. All right, how many non-zero diagonals? So now you have the central point. You have east and west, north and south, and top and bottom. So you have 7, right? Okay. So you have 7 non-zero diagonals. Okay. All right, so now let's calculate the space complexity of storing a full dense matrix, storing the zeros as well. We're going to go and calculate some numbers to storing everything in the matrix versus not storing everything. Now, to store everything, we already answered that question. If you were to store all the entries, you have to store all of these n squared, or all of these n squared by n squared, or all of these n cubed by n cubed, right? So this would be the number of elements that you're storing, because you're storing all the entries in the array, right? And these are the total number of entries. Okay, what about sparse storage? In 1D, what is the number of, roughly, okay, what is the number of non-zero entries? So you only have, where are the non-zero entries? On the non-zero diagonals, right? How many non-zero diagonals do you have? 3. So on roughly at large n, how many non-zero entries are you going to have? 3n, right? I know there's n minus 1. Forget about that. That doesn't matter, right? Large n. So yes, roughly it's 3n. Okay, what about 2D? 5n? Ah, yes, because we have n squared by n squared. So the diagonal, the number of entries on the diagonal is n squared, right? That's what trips you, okay? It's 5n squared. Okay, what about 3D? 7n cubed. Good job. Yep. Because the 3D matrix is n cubed by n cubed. The diagonal is n cubed, right? This is a square, right? The diagonal is n cubed, and it has n cubed entries. And 7 diagonals, we're going to roughly assume they're all of the same number of elements. They're going to be n cubed minus nx. It doesn't matter, right? Roughly at large n, n cubed is going to dominate. Okay, so now grab your calculators, and I want you to compare. So now you have you have the number of entries that you need to store for a dense matrix and its equivalent sparse matrix. These matrices are the same, except here we're storing it as a dense matrix, and here we're storing it as a sparse matrix. So here we're storing n cubed by n cubed, and here we're storing 7n cubed. So I want you to do this for 3D, so these two cases only, and give me in megabytes or gigabytes how much memory this is going to occupy. In Python, in our standard for floating point precision, memory occupied by one floating point number is 8 bytes. You store 10 floating point numbers, you have 80 bytes, okay? So go ahead, calculate the number of megabytes or gigabytes that you get with n equals 16, 32, 64 for a dense storage representation or a sparse storage representation of this 3D matrix, okay? Remember, 1 kilobyte is 1024 bytes, so your answer is going to be in bytes. Divide by 1024 to get kilobytes. Divide by another 1024 to get megabytes, by another 1024 to get gigabytes. All right? So start giving me some numbers. For this guy? What did you get? 2048 what? So convert to megabytes. So divide by 1024 kilobytes and another 1024. Kilobytes, and then another 1024 to get megabytes. You probably want to write down. That doesn't make sense. For the dense? No, wrong. 16 what? Megabytes? Nope. Come on, guys. So remember, it's this guy. And we are doing a 3D case here, 3D Laplacian. Yes, 3D, the 3D Laplacian. Okay, so the 3D case. So 16 cubed by 16 cubed by 8 bytes would be the answer here.
For 32, the dense I got 32, well, yeah, about 32,800 gigabytes.
32,000 gigabytes? That doesn't make sense. calculator. Grab your calculators. Okay, can someone run these numbers for me? Let me grab my marker. 16 gigabytes? That's not right. That's not right. So for the first one, for the n equals 16, what is the number? What is the number of entries? It's 16 cubed times 16 cubed, and the memory is times 8 bytes, right? So what is that? Just give me this number.
13 cube or 16 cube by 16 cube is 16,777,260.
Times 8.
134,217,700.
Okay, divide by 1024.
Divide by 1024 again.
Uh-huh.
128
Megabytes.
megabytes. Sorry.
Yep. 128 megabytes. Okay. Now do 7n cubed. So 7, so sparse will be 7 times 16 cubed. So that answer is in bytes.
229,376.
Bytes.
Yep.
Okay, convert to megabyte.
0.219.
Megabytes. Okay, do 32 now. Come on, guys. Okay, do 32.
I think I got 8.
8 what?
8
Gigabytes, okay. What about the sparse version? So 7n cubed, so 7 times 32 cubed times 8 over 1024 over 1024. Okay, that's right. Okay, so this is what you get. For 16 grid points in 3D, so 16 by 16 is 16, the dense representation of the same matrix occupies 128 megabytes. The sparse representation occupies 0.22. Just going to 32, doubling the number of points in each direction, you go to 8 gigabytes. This one, I couldn't even load it up on my computer. 512 gigabytes only for 64 grid points. It's nothing, 64 grid points in each direction. It's nothing. But look at the sparse version, 14 megabytes. That's like that's like the smallest picture on my iPhone, right? So you can see the importance, and you can see how important large n is, right? When n becomes large, and here we are overestimating this number because we're counting the diagonals as having n entries. So it's actually a little less than that. Okay, so you can see the advantage of using sparse matrix storage just from the space complexity. The pure advantage of storing the full matrix. Now, we haven't stored the matrix yet, right? Because we dealt automatically with solving the system just point-wise. But to make an advance, we will see we will have to store the matrix so we can use some more advanced solvers. The solvers we used were very slow, okay? All right. So you remember this in Python. There's two ways to build these banded matrices, whether tridiagonal, pentadiagonal, or 7 diagonals. Okay, there's one way that we learned, which is through the diag function in NumPy. And we said we built the diagonal as an array, as a one-dimensional array or just one vector, and we place it on the diagonal that we needed to. So the main diagonal has mostly 2's in it, except at the endpoints, we build mostly 2's and of the correct size, and we use diag to put it on a matrix. So we discussed this at the beginning of the course, right? But the curse of this diag function is that it creates a dense matrix representation. So it will, in the end, store it as a dense matrix, which for large number of points, for going to 2D or 3D, is not going to be efficient, okay? I discussed this early on, so we just build. For small systems, always do this. This is fine. It's easy and quick, okay? So today, I want to talk to you about how we can use something similar to build a sparse matrix representation of the same matrix. And this comes from scipy dot sparse module. Okay, so this is wrong here. This should be from scipy dot sparse. Actually, no, keep it. Never mind this. Okay, so because scipy and numpy work together very well. Never mind. Sorry. So the way to build this is you build your diagonals just the same way we did previously with diag. Just build them as 1s or 2s and whatever, fix the boundaries, whatever you want to do. But instead of using numpy.diag, now you use scipy.sparse.diags. And then give it all the diagonals you care about, all the non-zero diagonals, as a list here. So here I'm putting the main diagonal, upper diagonal, lower diagonal, followed by a list of the location of these diagonals. So this is the main diagonal. It's located at index 0. Upper diagonal located at 1 in the matrix. Lower diagonal located at -1. You can swap the indexing here. You could put LD, D, UD. You just swap the indexing. It automatically figures it out. So this is the minimum number of requirements to use scipy.sparse.diags. And then you have this format thing. I don't want you to worry about that, but this has to do with the internal representation of how scipy is going to store these sparse matrices. I used to do this in C++. We didn't, like, back in the day, you're talking like, maybe 10 years ago, we had to hard code all of this. And the way we did it was to say we would store only the non-zero entries, like as 1D arrays. So main diagonal, upper diagonal, lower diagonal, nth upper diagonal, nth lower diagonal, and we're talking 3D. And I would store an associated array for each one of those that contains the index location in the matrix, the ij location in the matrix. That's how it's done. So internally, Python is doing the same thing. Okay? Now, this format is whether you want to store row-wise or column-wise. So okay, this is compressed row storage, and there's compressed column storage, and a bunch of other features in that. Don't worry about it. Use CSR and move on. If you want to dig deeper into this, get into the weeds, but it's not going to matter for us for structured grids and for what we're doing here. Okay? Okay, this is great. So now you can use this to build that 1D problem. Okay? Now we haven't talked about the two-dimensional matrix. Oh, not the two-dimensional matrix. That's wrong to say. We haven't talked about the matrix representing the 2D or 3D Poisson equation. Okay? Last time when we left off, when we did the finite volume Navier-Stokes, I told you I'm going to represent the coefficient matrix, east, west, north, and south coefficients with their own arrays that look like the boundary, right? And then apply boundary conditions on those and iterate with SOR. And I told you I need that for what's coming next. So I'm going to use the same technology. I'm going to call that technology. Because if you think about the 1D problem, what did we do with the 1D problem? With the 1D problem, we built the diagonals. Okay, and they were 1D. We built the diagonals as 1D arrays. Then we set the boundary conditions. We forgot to set it here, but you go logically, you say, oh, at the left, this is what's going on. At the right, this is what's going on, right? And we set those coefficients and then rolled them into the matrix. Now I want to do the same thing with the two-dimensional or three-dimensional. Okay, I'm going to just spit out the code for you, because it will take me probably a lecture to explain how this is derived. But what I will do is the same procedure. I'm going to represent, I'm taking a two-dimensional. This is very relevant to us, so you will use this code from here onwards. But here's how it's done. We represent at each grid point in the finite volume sense or the finite difference, there's an east, west, north, and south coefficient and a p coefficient, right? So I'm going to represent each one of those coefficients as a full array that is consistent with the grid. It looks exactly like the grid, like we did last time, ny by nx, okay? And so this is it. For example, the east coefficients at each point, there's an east coefficient, and that array of east coefficients is of size ny by nx. So I can go and say at 0.52, the east coefficient is this much. At 0.67, the east coefficient is that much. Why do I like this technology? Because it allows us to reason logically about boundary conditions. I say on the left, there's no east, I don't care about a boundary condition on the east coefficient, so I don't do anything. But on the right wall, all the east coefficients are 0. So I go and set them all to 0. Rather than having to go into the matrix and say, here's the east coefficient for this point, and the west coefficient for that point. Does that make sense? Right? Because traditionally, the way these are built, you loop over the grid points, and for each point you ask, what is my east, west, north, south, top, and bottom coefficients? What entries, ij, do they correspond to in the matrix? And you go fill that entry. So it's a for loop. Okay? You can still do that if that makes more sense to you. But this is much faster. And to me, it's much, much more logical. Same thing for all the south coefficients. Same thing for all the north coefficients. Same thing for all the west coefficients. I didn't do anything yet for the p coefficients because AP is the sum of all of those. So I need to apply the boundary conditions first and then sum them up. And then you say, OK, so for the left wall coefficients, say for the example where we have walls or a fixed Dirichlet condition, then the west coefficients on the left wall are 0. The east coefficients on the right wall are 0. The north coefficients on the top wall, remember the north, on the top wall they're 0. And the bottom coefficients, the south coefficients on the bottom wall are 0. And then I add them up to create an array, not a matrix, an array of the center coefficients. So I now have an array for each one of those coefficients, array for the east, array for the north, south. And this is just a logical way of thinking about the coefficients for each equation. It's simple. Again, think about it this way. At each point, you're asking, what is the east coefficient? Most of them, they're going to be 1 over delta x squared or 1 over delta y squared, right? Except at the walls. OK, so now you're done. You have the list of all of these coefficients, what they're going to look like. The next step, and it's perhaps the one that is going to be the most kind of challenging for you to accept, but you'll accept it. We can work through this later in help sessions. Or you can actually be a nice homework assignment to ask you, why does it look like this? So next, what I'm going to do, I know that these coefficients, like when you look at the full matrix, the main diagonal contains all the AP coefficients. Okay, now this AP is of size ny by nx. But in the matrix, it is of size nx times ny. So it's a one-dimensional array in the matrix, right? It is a 1D vector, a 1D array. So what can I do to convert AP to a 1D array? I use a feature in NumPy called reshape. So I'm going to take that AP matrix, AP array, of size nx, ny, or ny, nx, and reshape it into a one-dimensional array of size and of the same size, but it's one-dimensional. So what this does, it will take the first set of points and take the second set of points, put them behind them, the third set of points, and put them behind it to make a one-dimensional array. That makes sense? Because we're assuming we're visiting the grid starting from point 0, 0, point 10, point 20. So it takes the first set of points, take the second set of points, puts it behind it, and it will create this entire array over here. OK. Yes, it's sequencing them, right? Because this AP looks like the grid. It's laid out like the grid. It's going to take it's going to keep the first set of points, take the second set of points, put them behind, because in the end, our solution vector, that's how it's sequenced, right? Our solution vector starts with the point 0, 0, and then 1, 0, 2, 0, 3, 0, 0, and then you go back to the next one, and so on, right? We lay them back next to each other. So that's how this reshape is doing. OK, so now the challenging parts are going to be, what do you do with the first upper and first lower? The first upper corresponds to the east coefficients, and the first lower corresponds to the west coefficients. Okay, but we know that those are going to be, they're going to be of size n, but they're going to be of this size, whatever this is. Let's call this the number of entries here n, which is nx times ny. So they're going to be of that size, but minus 1. There's one less entry. Okay, one less entry. And so you do a reshape, but on the east coefficient, you skip the last point. And on the west coefficient, you skip the first point. Why this is the case? It has to do with the grid. You're actually skipping all the points on the left side, on the right side at the end, or on the left side at the beginning. And same thing for the south and north. Probably should spend a lecture just to explain how I came up with these numbers. But I'm giving them to you. You can use this as is. It's a trick. The other option would be is to loop over every grid point and figure out where you are in the coefficient matrix and how to set the value. But then you'll get into trouble in creating a sparse matrix. This works for 3D as well. Okay, so you can extend this to 3D. You need to figure out what you're doing here is going to be nx times ny, and a little bit more complex, nx, and then the last one will be nx, ny. But then once you have these one-dimensional arrays, you just put them on the diagonals. The main diagonal, d0, the first upper d east, the first lower d west, the north diagonal and the south diagonal, which is going to be nx away in this direction and nx away that way. Okay, and then you place them like this, and you get that full sparse representation of the Poisson equation in 2D. Now, this is what we will be using when we go back to our finite volume solvers. So we're going to take, this is going to create a matrix, and that sparse matrix, we will use it with some really cool iterative solvers. We're going to be doing multi-grid. We're going to be doing conjugate gradient, sparse solves. It's a really bulletproof way of thinking about how to build that matrix for a 2D problem. I've avoided it so far because SOR and Gauss-Seidel, they're pointwise. But the advanced solvers, they need a coefficient matrix. And this is the way to do it. Yeah?
So AP is the matrix.
It's the array.
The array AW plus AE, AN, AS. So what AP dot reshape does is it takes each row and stacks them in.
Next to each other. Yep. If you think about it physically, okay, so say you have this grid. A2, A3, or what it does A0 dot 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 A3, and then A4 dot 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 to A7, and so on. Okay, it just stacks them next to each other because those will be the coefficients on the main diagonal. Okay, why is it like that? Because we chose to store our solution as phi0. This is our first in the solution vector. We're going to store them as phi0, phi1, phi2, etc. because we're counting x and then we count ny. Now, if you were to say, no, I want to count ny first. So you go phi0, phi1, phi2, phi3, phi4, phi5. That would you have to reshape in a different way. Okay? Now, the index, now this index here for the east coefficients, okay, if you think about it for the east coefficients, okay, this guy has an east coefficient, this guy has an east coefficient. This guy, there is a variable behind it. So the east coefficient, we set it to 0. But when you get to the end, there's no more unknown in the column vector. So you need to cut that off. Okay, now same thing when you go to the south coefficients, okay, all of the south coefficients, there's no variables at the beginning here at the bottom one. There's no variables to say, oh, this is p minus 1 or p minus 2. So you chop them off. That's the only way, that's the trick for it, to convert from this full array into that diagonal. Okay, so you get the right size. So all of these have south coefficients, okay, but this one, okay, we could say that the south coefficient is 0, but there's no, okay, so let me think here, yep. So the south coefficients, this guy doesn't, although we say, yeah, the south coefficient is 0, but there's nothing on the south. There's no variables in the south. There's no array, unlike the coefficient at this point, the next variable is this guy. So we say the east coefficient is 0 because it connects it to that guy, right? And it's 0 times that guy, it doesn't matter. But when you get to this point, there's no more variables behind it. There's no more grid points, so that's why we trim it at the end. And same thing for the west coefficient. There's no coefficient here. No west coefficient here. So we need to cut that off. Okay, so that's why I cut it at the beginning for the west coefficient. That's the little trick here. to do this. But once you accept this and figure it out, it's a piece of cake. This is the code that we're going to carry moving forward. Works for weird and x and y, whatever you want, okay? But then it builds a sparse representation of that matrix. So now if you take this and do a Lin algebra solve for the sparse matrix, it will solve. It will give you the Poisson equation in 2D, okay? Okay, now it's time to talk about, okay, so far we did space complexity. What did we learn? We learned how to count, how to multiply, how to use our calculators, okay? And we learned that dense matrix representation, for the same matrix, if you store it as a dense matrix, it's immensely more expensive, beyond, it's orders of magnitude more expensive than storing it as a sparse matrix. So we fixed the space complexity problem by using a sparse matrix representation, okay? Time complexity is more complex to handle, because then that depends on the algorithm that you're using to obtain the solution. Okay, so first I want to show you the cost of linear solvers. So this is a problem that you will do in your homework to reproduce the same results that I'm going to show here. I'm taking the Poisson equation in 2 dimensions, so n points in x and n points in the y direction. So del squared u equal s. You discretize this in finite difference sense. And the right-hand side is just a bunch of random numbers in the domain. So they're all going to diffuse to 0 eventually, okay? And I ran this. So I built that matrix. And I ran it with a inverse solver and a bunch of other solvers we're going to learn about. Okay, and this is what and then I plotted the time to achieve a certain tolerance versus the number of grid points, okay? And this is what you get. So on the y-axis is how much time it took to achieve the solution. The blue line represents the one of using A inverse, okay? The other lines are so-called iterative solvers or faster methods, okay? And look at the difference. And this is, on the x-axis, I'm showing the number of points in each direction. So once I hit 32 or 64 squared, I couldn't solve the problem anymore. You have exponential time for this using A inverse. I couldn't get any more data. The next one was the conjugate gradient method. You've probably heard of that word. Look at that. It scales really well. You get to 300 squared. You're still about 1 second to achieve the tolerance you want to achieve. And then, you know, it starts kind of growing exponentially. Then you have this black line. Now, this black line is unique. I call it here SP solve. So that's one of Maher's favorite solvers. It's SP solve stands for sparse solver. It is like an exact solver for sparse matrices, but it's not really exact. They use what's called multifrontal method. It's like an iterative method, you know. No, I don't even know what it is, right? But it's a little faster than the conjugate gradient, surprisingly. But the best one, look at this guy. This has a fixed time complexity almost, or like an order, 1? And this is the algebraic multigrid solver. Okay? That's what you want, right? You want a constant, a fixed cost, regardless of the number of grid points. So here you have 500 squared equations. 500 squared equations, right? It's a lot of equations, okay? And it's still like half a second. Now imagine you have to do this 1,000 or 100,000 times. It's going to matter, right? Because you're trying to advance the Navier-Stokes in time, and you have to solve this equation at every time step. So this really, really matters. Getting a small cost for your linear solver is very important. Okay. So now you can visually say that the time complexity of this algorithm is better, superior to this one, to that one, and to that one. Okay? All right. There are 2 general solution methods for linear systems of equations. And we generally distinguish those between direct methods and iterative methods. Direct methods are the most robust methods. They will solve any system of equations, whether it's sparse or dense, tridiagonal, pentidiagonal, whatever you throw at it. They are very robust. they give you an exact solution, okay? 0 error beyond round off. They give you an exact solution, okay? So there's no tolerance setting for an A inverse. So the blue curve I showed before, there's no tolerance to it. It's an infinite precision up to round off error. So 10 to the minus 16, let's say, okay? But they are expensive, as the first plot showed you, because their time complexity is insane, okay? Order n cubed generally, or order n squared. Iterative methods, on the other hand, they are effective and much cheaper for sparse matrices, for matrices that have mostly zeros in them. And we like to use them because although they don't give us an exact answer, but that's fine because we already are in the world of approximation. It's like the comment I made last time. You're solving the non-divergence free problem very accurately, right? And so, like, what's the point? You have so much error in the divergence, right? So you might as well relax your tolerance, right? So same thing here. It's like, yeah, you know what? Iterative methods, although they're not going to give us an exact solution, they will get very close. Typically, in our production codes, we set our tolerances 10 to the minus 7, 10 to the minus 10 tops, okay? That's kind of the lowest tolerance we set, and then move on with life, and that's acceptable, okay? Now, the choice of whether to use direct or iterative methods largely depends on the coefficient matrix A. So here's a diagram that I show in my numerical methods class, and it kind of splits and makes a nice dichotomy about these problems. If the coefficient matrix is small, just use a direct solver. So what's a direct solver? It's A inverse or numpy.linalgebra.solve. Okay, that's it. Just use a direct Gaussian elimination. Okay, don't worry about it. If you have 100 equations, 100 unknowns, and you're doing this once, just use a direct solver. You know, don't come to my office and ask me how to solve a 10 by 10 system with a conjugate gradient method for one time. You don't need that. Okay. Now, if your coefficient matrix is large, then you have two options. If it's dense, then you would need a special direct solver because we don't have iterative solvers for large, dense systems. Okay, so you need a special direct solver, gradient descent, or some other methods. Okay, this could be the issue with like big machine learning models and big data where you have a lot of dense, large matrices. So you need to figure out there are other ways for these dense, large systems. But for CFD applications, what we care about, you have a large coefficient matrix that's sparse. Okay, now, if the matrix is tridiagonal or pentadiagonal, you can use very special direct solvers that are very, very fast. The tridiagonal matrix algorithm or the pentadiagonal matrix algorithm. The advantage of those is they give you an exact solution, and they're fast. But beyond limited applications, they are generally useless, okay, for practical applications. So we end up with doing an iterative solver. Okay, so that's how I would make my decisions. Okay. Direct methods, this is a summary slide just for completeness, involve Gaussian elimination, which is just a standard method that we learn in high school and early linear algebra. There's factorization methods. You split the matrix into lower and upper matrices, but they are expensive. TDMA, pentadiagonal solver, or fast Fourier transform solvers, they're efficient, fast, but very limited application. Okay, they're not robust. Okay, they're robust only for those problems, but they're not for general CFD. If you want to use full direct methods for general CFD, that's insane because they're very costly. So the only robust methods left for us are general iterative solvers for sparse methods. Okay. Now the general iterative solvers approaches range from simple Jacobi methods like Jacobi, Gauss-Seidel, successive over-relaxation, to some very complex stuff like Newton-Krylov methods and multi-grid methods. We will touch upon those a little bit, at least the theory of those. We will only look, though, at the simplest iterative algorithms. The great thing about Jacobi and Gauss-Seidel and SOR is that we have analytical solutions about how the cost of the algorithm. So they are great examples to think about how iterative solvers work. So we're going to use those to develop a theory of iterative methods. And we use them when it's faster to solve iteratively. Now, there's a little trick that I didn't mention. There's a little condition, not a little, it's an important condition for a sparse in iterative solver to work, is that the matrix needs to be diagonally dominant. And what that means is that the diagonal coefficient, so take any equation, take any row or any equation in your matrix, the diagonal coefficient on the main diagonal needs to be larger in magnitude than the sum of all of the off-diagonal entries. Otherwise, you will diverge. Thankfully, in all cases we're dealing with, this condition is satisfied. Now think about the Poisson equation. We had 2 in the middle and 1 on each side. So this condition is satisfied. But if you had 2 and 1 and 2 on the other side, this condition will break the iterative solver. Okay? So you need to have most of your entries. You need to have this condition satisfied for all your equations. Sometimes you have a couple equations where that's not satisfied. You can say it's okay. But if this is not satisfied in general, your iterative method will not work. There are ways to rearrange the equations to make it diagonally dominant. You just change the order of the variables. And then, that's one way to go. That's called pivoting. But thankfully, for the Poisson equation for the pressure, we don't have to worry about this. Because by construction, the main diagonal, okay, is by definition equal to or larger. Remember, it's the sum of all the other coefficients, right? So it's by definition giving us that lower bound. It's by definition, AP is equal to the sum of all of those in magnitude, okay? Now, okay, so you're talking about pivoting, etc. All right, iterative methods. Okay, so I mentioned this. I already mentioned this. All right, so I will start with this, and then we will continue on next Tuesday. But let's revisit the elementary iterative methods. I'll do this slide, and then I'll let you go because I have to revisit it. We need to do some coding together. But remember, the Poisson equation was given by this discretization: finite difference, finite volume. It looks the same, okay, with some source term on the right-hand side. Now, for simplicity, I'm going to make delta x equal to delta y because in this chapter we are studying the properties of linear solvers. So I'm not worried about grid resolution right now. I want to simplify the equations so then we can reason about them rationally. All right, so if you put delta x equal delta y and set that equal to h, that equation simplifies very nicely. And then you see how the main coefficient, the main diagonal coefficient 4, is equal to 1 plus 1 plus 1, which satisfies that sparse system diagonal dominance condition. Okay, so now with this equation, we rearrange. We say Pij is equal to the average of all of the other coefficients minus that h squared s. And then we talked, remember, we had 3 methods that we discussed. Jacobi method, which essentially said we solve unknown ij using all the other unknowns from the previous iteration, and then we advance 1 point at a time. The Gauss-Seidel said, well, you already solved for point 1, so let's use that most recent value for the next point, and let's keep using the most recent values, and that results in almost twice the speed for convergence, and we will prove that with math. We'll prove mathematically that Gauss-Seidel is twice as fast as Jacobi for the Poisson equation. And SOR had this weird coefficient beta. You see in this homework that I released this week that you're going to study SOR on the diffusion equation, on the Poisson equation in 2D, and study the effect of beta. You're going to fix the error tolerance. Okay, say I want to achieve an error tolerance 10 to the minus 3, and vary beta, count the number of iterations to get us to that tolerance. And you will see for different values of beta, you're going to get an optimum value for beta, where you can get the system solved in 20, 30 iterations versus 200 or 300, right? And that's the mystery of this SOR. Again, we're going to analyze this with math. We're going to understand why this happens. All ties back to the coefficient matrix and its eigenvalues, okay? All right, I'll let you go here today. We have plenty of time on Tuesday. Come ready, we're going to do some coding on Tuesday. We're going to do some theory for iterative methods. Brush up on your usage of calculators. We're gonna be pleased. And so there's videos on YouTube. Sorry, it's just Couldn't stop. Okay, there. But brush up on some linear algebra if you want a little bit on eigenvalues. You know, if you just a reminder of eigenvalues, what they mean roughly. Okay, because we're going to talk about them next time. All right. Thank you so much for your attention. You have a nice weekend.